let me just quickly discuss what I prepared here. It's all the major formulas, ideas that we've discussed after the first midterm exam, and which is going to be on the second midterm exam. And this will be like my reference board. So here I'm going to solve problems about this or that, and it's useful, so I can say, guys, you see, we need to use that. We need to use that, right? I found it very useful, and I've been running exam review session in this format. All right, so let's just quickly discuss this. So after the first midterm exam, we started introducing the alternative method or approach to solve problems, energy approach, right? You remember we spent like I don't know, a couple of weeks doing that. And in that approach, we replaced vector quantities with scalar quantities. Instead of electric force, we introduced electric potential energy, and instead of electric field, we introduced the electric potential, right? So electric potential. We most of the time use two systems. It's either parallel plate capacitor or point charge. All the time, you notice that, right? So electric potential inside of a parallel plate capacitor. We derive these formulas properly. So electric potential is the value of the electric field times S. S is the distance from the negatively charged electrode of the capacitor, right? So V equals E times S. So that's the formula which can be used to find the electric potential inside of the capacitor. Then the second system, point charge, of course, it creates an electrical aura, which can be described using either electric field or the electric potential. Electric field was in the first exam, now it's electric potential. So the electric potential at any point at the distance r from the charge, which creates this electrical aura, can be found by using this formula. Again, we derive this V equals, again, V it's electric potential, V capital, K, universal constant, Q, and divided by R, right, where R is the distance from the charge, the source of the field, to the point in question, right? Then, and we introduce potential, right, using this formula, that and that, of course, using this formula, it's electric potential energy divided by the probe charge. So now, if you, for example, have information about the electric potential and you want to find the potential energy, so what can you do? Just solve this formula for U. U will be equal Q times V. So take Q, multiply by this V, it will be electric potential energy over charge inside of the capacitor. If you take, if you want to know the electric potential energy of the charge in the presence of this charge Q capital, take this Q, multiply by that, and you will get the formula for the electric potential energy, right? So after that, after introducing the electric potential and potential energy, we, of course, discussed how to move back and forth between the vector quantities and scalar quantities, which we use to describe the electrical aura, right? How can we move between E, which is electric field, and V, which is electric potential, right? So in order to move from the electric field to the electric potential, we use this integral. Again, it was derived properly, we practiced it, and of course, instead of integrating this function, we decided that for our problems, which are usually one-dimensional systems, right, we can just calculate area, because what is the graphical meaning of an integral? It's a area under the curve. If you plot E versus X, that's what I have here, E versus X, let's say that is the function. So then this integral is just the value of this area between the final point and the initial point, right? And of course, don't forget about the minus. So this delta V equals minus area under that curve. Okay, again, we practice that. And then what about reverse direction? What if you have information about V, and how can we get E? We derive this formula. Pretty much it's just E sub X equals minus dV over dx. You just, if you have a plot V versus X, you just need to find the slope, add minus in front, and that will be the value of the electric field at that particular point. And of course, if you have two-dimensional, of course, you can do the same for the y component of the electric field. But in our problems, all the time, they are one-dimensional. So usually we just need to use that. So after this, after finishing introducing energy approach, we went into simple circuits. we introduced the idea of the battery. Then we started introducing idea of capacitance. So how did we introduce capacitance? If you have two electrodes, of course, all the time their absolute value of the charge is the same, but one electrode is positively charged, the other one is negatively charged. So plus Q, minus Q, and let's say potential difference between them is delta V. So then, by definition, capacitance is ratio of the charge, usually just charge over a positive electrode, divided by the potential difference between those two electrodes. Of course, we've used this formula a lot. And then if you apply this formula for a parallel plate capacitor, you can get this. C equals epsilon naught universal constant times area of the plates divided by the spacing between the plates, right? Again, so that's what we used in to solve problems about capacitance. Then we started looking at more complicated circuits, right, full of capacitors, and of course we introduced the method of an equivalent capacitance, right? So in this case, if capacitors are connected in series, this is the formula which can be used to calculate equivalent capacitance, right? Just dealing with reciprocals, right? And important piece of physics. So charge in the equivalent capacitance, okay, in the charge of the equivalent capacitor equals to charges in capacitors connected in series, right? And you remember you had a quiz where you used these formulas, right? And use this method. So then if capacitors are connected in parallel like this, then formula is very simple, which can be used to find equivalent capacitance. You just need to add values of capacitors. And then important piece of physics, potential differences across equivalent capacitor equals to the potential difference across capacitors connected in parallel, right? Okay, so then after this, we started introducing some basic ideas about current, right, in order to actually discuss circuits. So we introduce current. So if you have a wire, and if you apply potential difference, of course, current is going to flow. Potential difference is the reason, current is a consequence. So how can we measure or calculate or introduce current? You take cross-sectional area, right? Okay, take cross-section of the wire, and measure the amount of charge in some period of time dt. Let's say the amount of charge is dq, which cross that cross-section in this period of time dt. So if you take a ratio dq over dt, that's what by definition, again, by definition, that's what current is by definition. Right. Then, of course, we introduce Ohm's law, which is basically relates potential difference, which creates the current, and current, which is created by that potential difference. So if you take a ratio of potential difference versus current, that ratio will be all the time the same if you don't change anything about the conductor. And that parameter we called resistance. So resistance equals delta V over I. So then we looked inside of this R in order to have some formula which can be used to calculate, for example, resistance of some resistor, right, which has a cross-sectional area, length, and which is made out of certain material. And we established that R resistance equals resistivity times length of the resistor divided by the cross-sectional area of that resistor, right? And we also introduce current density, which is current divided by the cross-sectional area through which that current flows. Right. Then, okay, so after introducing all these basic ideas about current, we started making circuits slightly more complicated, and we looked at the situations where resistors connected either in series or in parallel. And of course, we introduced the method of an equivalent resistance, right, which is very similar to this. So if two resistors are connected in series, then how can we find an equivalent resistance? It's very simple. You just need to add R1 and R2. An important piece of physics, in that case, current through the equivalent resistor equals to the currents through resistor connected in series, right? Then if resistors are connected in parallel, right, and basically this is the test to convince yourself that that resistors are connected in parallel, no, not in series, sorry. That is basically the test to convince yourself that the resistors are connected in series. If current through the resistors are constant all the time, those resistors are connected in series. Then, in the case of resistors connected in parallel, formula is less pleasant. You just need to deal with reciprocals, 1 over r, 1 over r, 1 over r, right? But that's life. And then important piece of physics, that potential difference across an equivalent resistor equals to the potential differences across resistors connected in parallel, right? So then, yeah, we practice this method, and after that, yeah, we spent a little bit of time discussing power, right? How did we naturally get to the power? Because in our life, we don't use electric form of energy directly. Every time we transform into other forms of energy, right? So if we transform it, of course, the natural question: so how much of energy do we transform? And we usually ask the question not just how much of energy do we transform, but how much per unit time, how much energy per unit time is transformed, which is power, right? So, and we show that the power equals to take a current, multiply with the potential difference. For example, let's say you have a resistor, potential difference across a resistor times the current through the resistor, and that will give us amount of power, in this particular case, transformed by the resistor, transformed into a thermal form of energy, into heat. Right? You know, also, using Ohm's law, we can rewrite this into I squared times R or delta V squared over R. Again, we practice it a little bit. So then, all right, just recently, we finished discussing Kirchhoff rules. Okay, Kirchhoff rules are basically, in terms of circuitry, they're universal. You can apply them in any circuit you want. There are no any limitations. R equivalent, C equivalent, they're limited to the cases when elements are connected either in series or in parallel. These rules, no limitations. You can use them to analyze any circuit. Right? So, junction rule. So if you have a junction point, then the total amount of current entering junction point must be equal to the total amount of current leaving that junction point. And loop rule. So if you take any loop in a circuit, if you start from a certain point, choose a travel direction, and if you move along that direction, counting all the potential differences, when you get back to the initial point, if you add up all those potential differences, you must end up with 0. Right? Conservation of charge is behind this law. Conservation of mechanical energy is behind this rule. Right? Okay, and just recently, in the previous classes, we discussed also RC circuits. I'm not going to review that because we just discussed it yesterday and a couple of days ago, right? I just wrote that just to remind you that this will be also on the exam, right? RC circuit and RC time constant, R times C. So pretty much that's the scope of the material that we need to know, and we need to know how to apply these in problems, right? Okay, so and after this, I prepared like 8 problems. Right? It should take about 2.5, maybe hours, maybe slightly more. Right? Again, guys, at any moment, ask me any questions. If you want to go. If you then want to come back, right? So no troubles. So first problem about energy approach. There will be 2 problems about how to use energy to solve problems. You know what? I will probably start labeling 1, right? So problem number 1. And what do we have here? Okay, let me grab my notes in order to see. We have 2 point charges. One of them electron, the other one is a proton. And a proton is stationary. Okay, let me draw it. All right. Yeah, I'll probably draw the picture and then I will write what is, if something is needed in terms of what is given. So let's say this is a proton. All right, let me write on top, it's a proton. So the amount of charge Q, of course, the charge of the proton we all know, right? And this charge, this proton, is stationary. Pretty much you can think like we're holding it. Maybe it wants to go somewhere, but we're holding it, so it cannot move anywhere. So I will just write down underneath it's stationary. Right. Okay, the second charge is an electron. At the initial moment of time, it is at infinity. So this is electron. right? And let me write, yeah, it will be, of course, charge is minus q. And at this initial moment of time, its velocity is v naught. And so since this is initial position, let me label it as initial. And this charge is at infinity. So initial distance between the proton and the electron is infinity. So let me label it as REI equals to infinity. Right. Right. Okay, maybe I can even show that this distance is right now R initial equals to infinity. Right. Okay, so then, so what is going to happen to this electron if it moves with velocity v naught? Of course, this electron is going to be attracted by this proton. But and again, of course, remember this proton cannot move. Maybe it wants to move that way, but we're holding it. So pretty much this proton cannot move. So this electron, since electron is attracted, of course, this electron is going to accelerate towards proton. Increasing, the speed is going to increase of the electron. So of course, it's going to become faster and faster and faster. And we actually want to know at which distance from this proton the speed is going to be doubled. For whatever reasons, let's say you want to know at a certain, you need to know the distance when the speed of the electron is going to be 2v naught. Okay, so let me draw something like this. Of course, it is going to travel, 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 travel. And let's say at this distance, velocity is going to be 2v naught. And what we need to find distance at this moment. So this will be our final, and I will put a question mark. Right. So this is our final position. This is initial, and that is a final. So that's the problem. Initial moment of time, initial velocity v naught, distance is infinite, and then the final position, velocity is 2v naught, and we need to find the distance between these 2 point charges. Okay, let me check if I gave everything. Yeah. So problems like this, of course, strictly speaking, can be solved again using 2 approaches. Either force approach, using Newton's second law, and then something else, or energy approach. In this case, using force approach is not the most convenient. The solution will be more complicated. In this case, energy approach is the best one. And plus, this exam is about energy approach. So force approach, we tested in exam number 1, right? So that's why, of course, I'm going to use energy approach. And of course, I'm going to emphasize on this. I will write in red. So energy approach. Right. And the energy approach, as you remember, is based on the conservation of mechanical energy, right? Since this force is conservative force, we can introduce potential energy, right? And in collaboration with kinetic energy, yeah, we can use conservation of mechanical energy to solve the problem. So initial point, of course, we need to just compare energies at the initial moment of time, or initial point and the final point. So basically, this is the beginning, right? And now we just need to dive deeper and deeper until we see everything, until we will be able to see what needs to be found, right? Okay, so now from here, of course, total mechanical energy, it's a kinetic energy plus initial, equals to K final plus U final. Right? So far, nothing fancy. And of course, kinetic energy, you all know which potential energy we will have to use. At this point, not many, but quite some students made mistakes. They use some wrong formulas. Which formula do we have to use? We have 2 point charges interacting. So potential energy is Q times this. Because some students use that, and of course that is completely wrong, because charge inside of the, in that case you will use the wrong system, charge inside of the capacitor. Of course, it's not what we have. We have 2 point charges interacting. So it's just a charge Q small times that, right? So potential energy it's K, Q small, Q capital divided by R. So, but of course, in our case, R small, I mean, Q capital is just an electron minus Q, right? So let me show that this is, of course, minus Q in our case, right? So potential energy effectively is going to be, okay, let me write underneath, it will be minus K Q squared over R, right? So be careful, because that's a place for typical mistake. So now let's write explicitly everything. 1 over 2 mv initial. Initial, it's a v naught squared. Then plus potential energy initial. Actually, what's the value of the initial potential energy? Initial potential energy, so it's at this point, initial position is infinity, right? When R goes to infinity, potential energy is 0. That's basically our reference point. You remember when you introduce potential energy, electric potential energy or gravitational potential energy, every time you need to tell people where is your reference level. In this case, in the case of this formula, the reference point is at infinity, point where the potential energy equals to 0, right? So, but anyway, let me write that down. So it will be minus K Q squared and R initial, all right, which is equal to infinity. Of course, this term is 0, right? Okay, so now final position, this K final, again, 1 over 2 m, and we know the final velocity, 2v naught squared, and plus potential energy. Potential energy, yeah, now R will be final, it's our unknown, right? So it will be minus K U squared over R final, right? You know what, I don't like that there's over here a mass of overlapping. Let me put some line separating them. Okay, so now what, given RF is unknown, pretty much one equation, one unknown, pretty much physics is over at this point. We just need to solve it for R final. That's it, right? So now let's just carefully solve it. Probably I do this. First, I will take this term to that side. This term will go to that side, right? Let me just move terms around. So it will be K Q squared. I'm just rewriting this, divided by R final. Move to this side. Here we had with minus. Now it will be with plus, right? Then this stays. It will be m over 2 4v naught squared. 4v naught squared, it's this term. And this term goes to that side with minus. So it will be minus m over 2 v sub 0 squared. Okay. My whiteboard slightly wobbles. I haven't used it for quite some time now. So, of course, we can subtract this, right? So it will be 3v naught squared times m divided by 2, right? So it will be 3m v sub 0 squared divided by 2. Okay, so now RF goes here into the denominator. This goes into the numerator. This goes to the denominator, so we can easily solve it for RF. Right. I don't think that I need to explain to you. So it will be this times 2, 2k q squared divided by this, 3m v naught squared. So I'm getting this. Let me check my notes to make sure that I didn't make any mistakes. Right. And 2k q squared. Yeah. Numbers, in this case, I didn't give, right, because I wanted to see in terms of a formula. So that's the answer. And usually students like problems like this, and most of the time students do reasonably well, except for occasionally they just use the wrong formula to calculate potential energy. Right. In this case, since charges have opposite signs, potential energy is actually negative, right? Negative potential energy. Right. Okay, any questions? Again, we're not introducing something new, something fancy. We're just refreshing what we already discussed in the past. Yeah.
I have a quick question in regards to the negative on the K. Is it because it's going towards the left?
No, it's just because this is an electron, it's a negatively charged object.
Oh, okay. All right.
That is the proton, positively charged object, right?
Okay.
Potential energy, it's a scalar function, which doesn't care about direction, right? It's sort of like no, kinetic energy is completely different things. It cannot be negative, period. Potential energy can be negative, right? So I wanted to compare with kinetic energy. No. Right. It's negative because this is the formula, and one charge is positive, the other one is negative.
Okay.
Awesome. Right. Okay, so that's the first problem. And now the next one. Conceptual, very quickly conceptual question. Very similar we had in our lecture. So let's assume, okay, it's not number 3, it will be just a conceptual question. I'm not going to label it as a problem. We have a positive charge, let's say here, Q capital, creates an electrical aura, right? Then there is an electron. Yeah, electron is moving along this trajectory. So let's say it's an electron moving like this. All right, so this distance is smaller than this distance. And we need to see what happens to the potential energy. All right, so what about the potential energy? Is it increasing, decreasing, or stays constant? Right? Well, let me write. So what's the question about? Increase or decrease or constant. Wait. Or constant. So basically, that's what we need to answer. Right? Okay, so first of all, which formula can be used to calculate potential energy? 2 point charges. This is the point charge. That is also point charge. Of course, it will be Q times this. It will be K, Q small, Q capital divided by R. Right? So potential energy is K, Q small, Q capital divided by R. Right. Potential energy, positive or negative? Okay, finally I lost my part of my antenna. Just a second. The cover. Again, I'll have to glue it back. Potential energy, positive or negative? It's related to actually one of your questions, right? When we solved the previous problem. This charge, Q capital, is positive. This is an electron, negative charge, right? So potential energy is negative. So potential energy is equals to minus K absolute value of charge of the electron, Q divided by R. So potential energy is negative, less than 0, because of the electron, right? See that? Then next step, it's a first step. The second step, we need to see what happens with absolute value of this potential energy. What happens with R as this electron travels this way. So this is our R initial. This is our R final, right? And of course, R final is larger than R initial. So R is increasing. And since R is in the denominator, when R increases, absolute value of potential energy decreases, right? Decreases. So, but potential energy is negative. So decreases, it means that our potential energy is becoming less and less negative. -2, -1, then -0.5. So potential energy becomes less negative. So it means what happens to the potential energy when it becomes less negative? It increases, because out of two negative numbers, which one is larger? The one which absolute value is smaller, right? So in this case, potential energy increases, right? So since R is going up, right, increases, then potential energy increases, right? So yeah, increase this. So occasionally I give a problem of this type among multiple choice questions. Trajectory can be more complicated, but all the time, two steps. First, see what's is potential energy negative or positive, and then see what happens with R, and then combine those two steps in order to get to the correct conclusion. Right? So you just need to be just careful. And yeah, some students make mistakes if they're not careful. All right, but most of students do reasonably well. So it's a quick conceptual question. And now, enough of this box. Now let's discuss these transitions between the electric field and the electric potential. Okay, now I need to start erasing this, and this will be problem number 3. All right. Okay, I can erase all the way to this point. So that's problem number 3 now. Okay, it looks like I need to change blue marker soon. So first, this problem. Okay, let me show what is given, and then we will understand which formula must be used. But of course, it will be from that box. So we have graph, which tells us how electric field changes with position. Okay, let me estimate the amount of space I need. So this will be E sub x, units volts per meter, right? It can be, you remember, units of electric field, either newtons per coulombs, or it can be easily shown that volts per meter is the same. Right? And right here, x, right, in meters, right? And it goes down. Then the graph is given. The graph is given, and let me first show the graph, and then I will put numbers. It will be easier, right? Graph like this. Okay, it's maybe slightly too steep, but it's fine. Then this point is what? 1 meter. Then 1, 2, and 3, 2 and 3. Then this value is minus 100 volts per meters. Then this point, at this point, when x equals to 3, the value of the electric field is 200. This will be approximately 100, right? So that's the plot. Which shows us how electric field changes with the distance. Electric field equals 0 over here, so it's again, guys, before we start even start solving the problem, what does it mean that electric field has a negative value? It means it points, because electric field is a vector, right? It's not a scalar quantity, it's a vector. Negative vector, it means it points in the negative x direction. So over this over this distance, electric field points that way. But then after point 1, electric field you see is positive. It means it points in the positive x direction, because again, electric field is a vector. And 0 over here. So then plot is given, and we also know, or given, that the value of the electric potential, V at x equals to 0, okay, this is 0 point, right, equals to minus 50 volts. So additional piece of information. So this graph is given, and this additional piece of information is given. So we need to calculate the electric potential at point 3. Again, we've done it in our recitation classes, but again, what we do, we just review it. So it will be fresh in your head. So we need to find, let me write, what is given is on the graph over here. So we need to find the electric potential when x equals to 3 meters. Right? So which bridge do we have to use? So we pretty much need to go from the electric field to the electric potential. So it means that we need to use this formula, which is basically connects change in the electric potential with the electric field. So pretty much we just need to deal with that integral. But of course, you remember, in our cases, instead of calculating integral, we can just calculate area under the graph, right? Carefully calculating area. And of course, don't forget about the minus in front. Calculate area and add minus in front, because area calculates the value of the integral, but we still have minus in front. So let's do it. So of course, first of all, we need to just rewrite the formula to show what we are planning to use, minus integral from x initial to the x final, ex dx, right? So let's even frame it, because that's essential. And so now we just need to make a decision which point will be our initial point and which point is going to be our final point. And again, that decision is based on what is given and what you need to find. Some information about the electric potential is given at that point 0, so obviously this will be our initial point. So let me write, so x initial equals to 0, and then x final, since we need to find electric potential at point 3, so that will be our final point, 3 meters. Okay, so pretty much all the preliminary steps are done. So now we just need to, first I will write, of course, an integral, and then I will show which area needs to be calculated. Okay, I will probably, all right, yeah, I have enough space. So delta V equals, I'm just rewriting this, it will be minus integral from 0 to 3 ex dx. Okay, after making a decision about the initial and the final point, I just wanted to rewrite integral. And so it is equal to, so from this point to that point, so we just need to calculate area under this curve. And which area, of course, we're talking about? This one. So first it's this area, and then that. Because sometimes, a few times I saw students making, okay, I wouldn't say silly mistake, it's kind of serious mistake. They calculated a wrong area. They would calculate area, this one, which is completely wrong. Area under the curve, it's the area between the line, the function, right, and the x-axis. So in this case, it's this area and this area, right, these two areas. Because I've seen in the past quite a few students just calculated wrong area over wrong sort of triangle in this case, right? So now, you know what, let me separate this part. Okay. So now it will be equal to minus what? Okay, let me label this point. Let me use different color probably. So this is point O, right? Then this point, let me follow my notations. This point is A, this point is B, this is C, and this point is D. Okay. It's useful to show those numbers. I mean, to show those points, to label those points. And so it's a minus area of what? Area of this triangle OAB, and then plus area of the triangle BCD. Area of B, maybe I can put a parenthesis, BCD, right? Okay, so let's calculate these areas, all right, and then take care of this delta V. So area of, okay, let me put equal, and I will continue this line over here. So minus area of OAB. Again, it's a triangle, so it's a 1/2 times base times height. Base is 1, this distance is 1 meter, right? So it will be 1 meter times height, and the height is negative. So as a result, our area is going to be negative. So times minus 100 volts per meters. So that will be the area of the first triangle. It will be negative. Then area of this BCD, the same. So again, it will be 1 over 2. Base now is 3 minus 1 meters, 3 minus 1 meters. And the height is CD, which is 200 volts per meters. Right? So now minus in front. Then this negative value will be 100 divided by 2, it will be minus 50, negative 50. And this is 2 over 2. This will disappear. 200 positive. 200 minus 50, it's 150 volts positive, and minus in front, it's minus 150. Yeah, okay, I'm getting the same in my notes. Minus 150 volts. So that's the potential difference. What we just calculated is potential difference. But so now let's open explicitly what is delta V. Okay, now I can erase this part. So delta V, so now this equals, of course, it's a V final. Final is 3. Okay, I will just use subscript 3. And of course, you understand the meaning. It just means the value of the potential at point X equals 3 meters. Then minus, because delta, all the time, it's a final minus initial at point 0. Okay, X equals 0. And equals to minus 150. Right. Okay, this I will move to that side. So this will be V at our point, which we want to find. This goes to that side with plus. Here it's with minus. There it goes with plus. So it will be V at X equals 0 minus 150 volts. Okay, so the final push. The value of the electric potential at X equals 0 is negative 50. So be careful when we move this term to the other side, and the value of the electric potential also negative. So sometimes students make those silly mistakes, losing one minus or adding extra minuses. Right? So it will be minus 50 volts, minus 150 volts. So as a result, we're getting negative 200 volts. Let me check. Yeah, minus 200 volts. So that's the value of the electric potential at point X equals 3. Typical problem. Again, we solved similar problems in our recitation classes. All right. It's not new for you. Okay, so move. Again, guys, if something not clear, tell me. So the next problem, yeah, it's very, very simple. But anyway, let's just quickly review that. I was just thinking, should I just squeeze it in this part of the board? No, here I'll have to draw a graph. Yeah, I'm afraid that I will not be able to fit. All right. Okay, can I start erasing? At least let me erase the figure so I can start drawing a different one. Okay, so if you're not saying anything, that I assume that you understood all the steps. All right, and I can erase this also. So next graph, and this is the problem number 4. So basically here we practice how to move from the electric field to the electric potential, and now let's move in the opposite direction from the electric potential to the electric field. So problem number 4, and what is given? Okay, let me grab my notes so I can easily redraw. So this is electric potential, of course, units of volts. Then X, not X, R, but instead of X, R is used, so what a big deal. So let's say R in meters, position basically. And the plot. Okay, probably first I will put numbers over here. 1, 2, 3, 4. I need up to 6. So 1, 2, 3, 4, 5, 6. Okay, enough. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. And now, based on this, I can draw a graph. So first, it starts from 0 and goes to maximum at 0.3. Oops. Right. Something like this. Then it suddenly drops to negative value at 0.4. The same value underneath. So this is 0.4, and here will be -4. -4. Okay. And over this short stretch of distance between 3 and 4, potential drops to negative value. Okay, it's supposed to be a straight line. Right. And then it stays constant up to this 6 point. Yeah, it looks like everything which we need is on the graph. Pretty much, yeah. So given graph is given. Right. So a graph is given. So what needs to be found? Actually, we need to calculate the electric field at every point and see where is the electric field at the largest, right? So the largest E. Basically, it means that we need to calculate electric field everywhere and answer this question. And of course, before I start, solve this problem, we can erase this. Information about the electric potential is given, so we need to move to the electric field. So it means that we just need to use this formula, right? We just need to look at the slope, add minus, and that's it. That's it, right? So let me first write. So we move from this to that, and so the formula is E sub x equals to the minus dv over dx. Of course, analysis must be split into 3 parts, right? Because here we have a straight line. Of course, it's easier to analyze this separately. Then this straight line also separately we can analyze. And then, of course, we can analyze that part. So let me label them. So it's region number 1. Then, you know what, let me write underneath. Here, region number 1. Then here, region number 2. And here there will be region number 3. Which is obvious, right? So region number 1, and you know what, before we start discussing it, actually calculating, look, how can I rewrite this formula? Since we have straight lines everywhere, so instead of using dv over dx, we can use delta v over delta x. Because what is this effectively? It's a slope of the curve. If you have a straight line, slope is exactly the same. So it doesn't matter if you're calculating the slope, if you use infinitesimally small increment delta x, very small delta x, or if you use finite delta x, if you use infinitesimally small dx, or if you use a finite delta x, the slope is exactly the same. We've used this trick already several times in this course, so again, it's not new for you. So I can write this as minus delta v over delta x. Right? Okay, that x I can write it better, right? And again, that is for straight lines, for straight lines. So we can use the trick. Okay, so now, yeah, we can use that. And so region number 1, between 0 and 3. Region number 1. So E1 equals to minus delta V over delta X. So what is final value? Okay, let me first write. So it's minus V final minus V initial, of course, divided by X final minus X initial. And so final value over this stretch, it's this value. So it's a 4 volts, right? 4 volts. We almost erased it. So it will be 4 volts, then minus from the formula, and the initial value is 0. Minus 0 volts divided by 3 minus 0. Oh, so it will be minus 4 over 3. Right? Volts per meters. Minus 4 over 3 volts per meters. Okay, let me check. Yeah, of course, it's correct. Okay, you see, very simple. Just calculate the slope and add minus in front. Then region number 2. All right, so it will be E with the subscript 2. And so now final is negative 4. Right? Okay, let me write minus delta V over delta X, and I will start immediately this. Minus negative 4, it's a final minus 4 volts. Then initial 4 volts, but since we're subtracting, right, so minus 4 volts, right, and divided by the 4 minus 3, right, the change in X, so it will be 4 minus 3 meters. Okay, everyone sees why I have here minus, because we're subtracting the final minus the initial. Initial value of the, or final value of the potential is minus 4, and then minus, and the initial value of the potential is positive 4. So we have minus 4, minus 4. So now if we calculate, we're going to have 8, just 8, negative 8, and then minus in front, so it's positive 8, right? Yeah, 8 volts per meters. 8 volts per meters. Okay, so now the last region, number 3, and of course in this case everyone can see that the electric field is going to be negative. Oh, 0, sorry. 0. All right, since V is constant, right, so electric field in the third region is 0 since V is constant. And like again, like in the previous problem, which I just erased, what does it mean that electric field in the first region is negative? You see minus 4 over 3. It's a vector quantity. It just means it points in the negative R direction. So over here, electric field points this way. Actually, I can even show it. So electric field E, this is region number 1. You see points that way. In the region number 2, electric field positive. It just means it points in the positive R direction. So over here, E2. And of course here, E equals 0. Right. Okay, so this is, yeah, really simple problem. Right. Okay, we can move it. Yeah, so the largest E, yeah, you can see, of course, in the second region, right? Because changes in V is the changes are the fastest in V.
I have a quick question.
Yeah.
Could you just repeat what you said in regards to the E and like the red that you highlighted? It's on the graph. I think the direction of the E. Yeah.
Yeah. Okay. You remember physics 1, at the beginning of the physics 1, usually we discussed one-dimensional vectors. What does it mean if you have one-dimensional vector which is, for example, positive? Let's say velocity is plus 5 meters per second. What does it mean? It means, because it's a vector, it points in the positive x direction. If velocity is minus 5 meters per second, what does that minus mean? It just points in the negative x direction, right? So the same here story, right? Because again, from the mathematical point of view, mathematics doesn't care if your vector is a vector describing velocity or describing electric field. Mathematics doesn't care about the physical meaning. There are some rules that those vectors must obey. That's it. So in this case, since our electric field, for example, over here is 8 positive value, 8 volts per meters, it just means it's a one-dimensional vector. It just means it points in the positive, in this case, r direction. Right? But if your vector, again, one-dimensional vector, because electric field is a vector, period, right? Nothing to discuss. If your vector, one-dimensional vector, is a negative, it just means it points in the negative r direction. Of course, it will point over here, points that way.
Okay. All right.
Of course, in this problem, it's according to what problem asks, this is not needed. All this my blah 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 about direction, right? Unless I ask in the problem, right? But I just wanted to remind what you saw in the past, right? And which is, of course, understanding of which is kind of important. Right? Okay, that's what I meant by drawing those vectors.
I have a
So,
question.
yeah, right.
How did
Probably I can
could
send
you
you an
repeat again on how did you get the relation for EX?
this or this
Yeah,
part? The first
or
one,
that
right?
one.
Oh, yeah.
The second
We
one.
derived it. The second one, this one.
Yeah.
Okay. Look, what does it mean, dv over dx in this plot, in this graph? dv over dx. You take small change in v, dv, and divide it by the small change in x. That is slope. The value of the slope of this graph, right? Mathematics, calculus. So dv over dx, it's a slope. And look, this is a straight line. Slope is exactly the same. It doesn't matter where you measure or how you measure the slope. Slope is constant because it's a straight line. So it means that, look, if you calculate that slope using infinitesimally small dx, or if you use finite, for example, delta x between this point and that point, slope is exactly the same. If you take this delta v and divide it by this delta x, you will have, let's say, minus 4 over 3. Or if you use infinitesimally small dx over here and infinitesimally small dv over here, the slope will be exactly the same, minus 4 over 3. But again, it's only true when you have a straight line. We use this trick already several times in this course. When the formula gives, in the formula you have something derivative, like in this case dv over dx, and we just replaced it with calculation of the slope over a finite, in this case delta x. Right. Make sense? Or not? Okay, it's a calculus, right? Basically, when you analyze functions,
Yeah, true.
how you analyze functions, right? Because the slope is constant. It doesn't matter if you calculate over finite delta x or infinitesimally small dx. But again, it's only correct for straight lines. Okay, enough of this box. So now next. Actually, I jump immediately into. I didn't prepare anything about capacitance. Probably I want to, I was actually thinking about mentioning only one thing. I think we had clicker questions about this, what I want to discuss, and also one problem in our recitation class. Okay, guys, imagine that you have a capacitor, which is first connected to a battery. Right? Capacitor connected to a battery. Of course, after a short period of time, this capacitor will be fully charged. And then, once it's fully charged and connected to the battery, and if you start changing the distance between the plates of the capacitor, let's say you increase the distance or reduce the distance, which quantity describing capacitor is going to stay the same? You remember when you analyze a capacitor, you need to think about three parameters. I mentioned it already a gazillion number of times. C, Q, delta V. Pretty much I'm asking which quantity is going to stay the same if your capacitor is connected to the battery and you keep changing distance between the plates. Capacitance will definitely change because you change the geometry as you change the distance. You change distance, capacitance changes. Then, what happens to the potential difference between the electrodes of the capacitor? Potential difference stays the same. Potential difference stays the same. When capacitor is connected to a battery, potential difference across electrodes of the capacitor, between electrodes of the capacitor, is constant. It doesn't matter what you do with the distance. You bring those plates closer or farther away, potential difference stays the same. And then, of course, charge changes. Charge changes because capacitor is connected to a battery, to the source, infinite source of an electron. So electrons can go into the capacitor, increase number of electrons in the capacitor, or they can go back into the battery. So charge changes in that case, but potential difference stays the same. But if you change the situation, so pretty much I wanted to emphasize, if a capacitor is connected to the battery, potential difference is constant. Of course, assuming that the battery is healthy enough, right? So it's not dying. Then, second situation, what if you charged already a capacitor? Right, so capacitor is fully charged, and then you cut the battery and remove the battery from the circuit. So now it's just only a capacitor, fully charged. And then you start changing the distance between the plates. You can reduce the distance between the plates or increase the distance between the plates, which quantity stays the same. Again, I mean out of these three, C, Q, delta V. In this case, charge stays the same. Why? Because those electrons which which are inside of the capacitor now are trapped there. Those electrons are trapped. They cannot escape from the capacitor, right? Maybe, of course, we assume that there is no humidity, so the electrons cannot escape through air or through you. So pretty much we assume all those conditions. So if we assume that, charge in the capacitor stays the same. It doesn't matter what you do with the plates. And of course, it happens when the battery is disconnected. Right? So then, capacitor charge stays the same. Of course, capacitance changes because you change geometry, right? Change geometry, capacitance changes, right? And then, of course, potential difference is going to change in this situation, right? So pretty much in these two examples, I emphasize all the time: if a capacitor is connected to the battery and you start changing distance, potential difference stays the same. But if you disconnect the battery and start doing the same, charge stays the same. Charge is trapped inside of the capacitor. Maybe those charges want to escape, but there's no way, right? Because they are trapped inside of the capacitor, which is basically isolated from the outside world. Right? And again, every time when you analyze a capacitor, think about three parameters: C, Q, delta V. Then about method of an equivalent capacitance. Since you just at the end of the previous week you had the quiz about the method of an equivalent capacitance, so I decided to skip that, skip reviewing that, because we just had a quiz about that. So now let's discuss this, and then method of an equivalent resistance and the other things. Okay, so now I can erase this. Time flies, almost 1.5 hours already. Okay, again, problem is not complicated. About resistance and current, and based on my experience, usually students do in these problems the best, right? Usually students are quite familiar with Ohm's law and how to play with that. Anyway, so let me write what is given. In this problem, let's assume this situation. You have a long wire, what, 46 meters long. It's basically a spool of wire, right? And let's say you don't know what is made of, which material is used to make that wire. So what can be done? You can set up a simple experiment. I don't know, take a small battery, connect it to the wire, right? Measure the current, you know the potential difference, right? And by measuring the geometry of this wire, you should be able to calculate resistivity. And once you know resistivity, you can look at the reference book. You can see which most likely material was used to make that piece of wire. Right. So this is sort of the idea behind the problem. Right? Okay, so let me write that down. I'll grab my notes. So we have a cylindrical wire. Okay, and what is given? Radius is given, I think. Yeah, radius. I think I used R small. Let me check. Yeah, R small is 2 millimeters. Then length is given, as I said, 46 meters. Yeah, it's definitely a spool of wire. And so then battery is connected. So let me write battery. And the potential difference across the battery is 3.7 volts. So once you connect the battery to the wire, of course, as a result, as a consequence, there will be current flowing. So current, let's assume you use the voltmeter, you can measure it. So current is 2.5 amps. Right. So we need to basically calculate resistivity and identify the material. Okay, I will just write down the resistivity. So what we need to find? Rho, resistivity. Again, you remember the difference, the major difference between resistivity and resistance. Resistance, it's a quantity describing a resistor, an object which has certain length, certain cross-sectional area made out of certain material. So that's resistivity. But that's resistance, sorry, resistance. But resistivity describes a material. Gold, a certain number, copper, a certain number, aluminum, a certain number, right? It doesn't matter what's the shape, what's the length, right? It doesn't matter. It doesn't depend on all of that. It depends only the material. Okay, so now let me sketch the situation. So let's say this is our, of course, I'm not going to draw a spool, too complicated. So that's basically my cylindrical wire, right? And it is connected to a battery. Right. So this is delta V. And then radius R is here, right? Length also given. That's our L, right? Rho, that's our unknown. And what else? Potential difference here. Current, of course, I can show that current, of course, flowing. So that's I current. Okay, so that's the situation. So here, basically, we have two steps. First, how can we find resistance using electrical parameters? We have the reason. We know everything about the reason of the current, potential difference of the battery, and we know the consequence. We know the current, the value of the electric current. So if you know the potential difference in current, of course, you can find resistance using Ohm's law, right? Okay, so that will be the first step. So resistance can be found by taking the potential difference and dividing it by the current. But from the other side, we can also find resistance because it has a nice cylindrical shape. We can also find resistance using this. Rho R equals resistivity times length and divided by A. Yeah. But from the other side, we can find resistance equals to rho L and divided by A. Right. So we can combine them because in both cases we're getting resistance. So we can write rho L divided by A equals to that. So rho L divided by A equals to delta V divided by current. So in this, everything is given except for rho. L is given. Cross-sectional area, of course, we can calculate. It's a pi r squared, right? So of course we can. All right. So A equals to pi r squared. Right. Area of a circle, basically, right? Of radius r small. And that is our unknown. Right. Okay. So pretty much one equation, one unknown, because the given, everything is given except for rho. Right. So we can solve it for rho. It will be equal to A goes over there, so it will be delta V times A divided by, okay, you know what, A, let me write immediately pi r squared. Pi r squared, and divided by L goes over there, so it will be I times L, right? So that's basically the expression. Of course, 2 millimeters is not good, so you need to convert it into meters, right? So let me emphasize on that. So it will be 2 millimeters equals to 2 times 10 to the power of minus 3 meters, right? Don't forget. Otherwise, you will mess up the units. All right, that's it. So if you calculate it all, you will get to, you will get that it is equal to 4 times 10 to the power 4 times 10 to the power of negative 7 ohms times meters. Okay. Again, it's usually this part is reasonably simple. Now let me look at now equivalent resistance. Since we didn't have a quiz about equivalent resistance, so let me just discuss a couple of problems. And after that, Kirchhoff rules. And then a little bit of power, and it should be enough. Okay, let me erase this. Start erasing slowly. So this will be now problem number 6. Okay, the configuration of resistors is exactly the same like you had a configuration of resistors in your quiz, okay, in the previous week. Right? You remember you calculated equivalent resistance. But now we will have to calculate equivalent resistance between different points. Okay, so first, let me draw it this way. Okay, the first one, then over here there will be, let me draw it like this. Then over here, then this, and resistor that. Yeah, and they have exactly the same resistance. All these resistors have exactly the same resistances. So R, 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 and R. So again, as I said, very similar, not similar, exactly the same you had in your quiz. But in your quiz, you calculated equivalent resistance between points. Okay, let me even show those points. So this point I labeled as B, this point A, and this point C. In your quiz, you calculated equivalent resistance between point B and C, and the solution was quite reasonably simple, basically in 2.5 steps. Now we want to calculate equivalent resistance between points A and C. So it means what? In your quiz, effectively, I can say that I connected my battery at points B and C. But now I'm connecting the battery, which is going to drive, I know, some current through this circuit. I'm connecting to points A and C. Right? Okay, I can even maybe show it something like this. So this is my effectively sort of like a battery. Right. So now equivalent resistance between points A and C. So we need to find, you know what? I feel like I need this space, right? I should have drawn picture slightly lower. Okay, I will write here in the corner. So what needs to be found? R between points A and C, right? Equivalent resistance, right? So it's a equivalent resistance. So that's why I drew the battery over here. Okay, let's see. So pretty much we just need to collapse all the system of resistors into a single resistor, which is going to be like this between points A and C. Pretty much we are not supposed to cross point A and not supposed to cross point C all the time. So let's see. Let's start. First, which resistors are connected either in series or in parallel? And again, you need to remember the tests that you have to use in order to convince yourself if an elements are connected in series or in parallel. In series, currents must be the same. In parallel, potential differences are the same. So in this case, out of these resistors, obviously resistor this one and this one, you see, there are no any junction points. It means that current is going to be the same. So these two resistors are connected in series. So I can sort of draw like this and write that they are in series. Right? And so now let me simplify immediately this circuit. Right. Well, I'll have to redraw it so many times. So then this stays there. This guy stays still here. And instead of these two resistors, of course, we're going to have an equivalent resistor. So let me label it. How did I label them? Just a second. I just labeled R equivalent 1. R equivalent 1. And of course, it will be equals to 2R, because when the resistors are connected in series, we just need to add their values. This is still R, and this is still point A, and this is point, oh no, it's C, not B, sorry. Point C. All right, so R equivalent 1 equals to R plus R equals to 2R. Okay, first step. Now, the next step. What else? Now, this resistor and this resistor definitely not in series because we have junction points, and of course currents are not the same. But potential differences. Potential difference between across this resistor and potential difference across that resistors are the same, because points above this resistor and points above this resistor, they belong to that piece of wire. So all these points are at exactly the same potential. Then points below this resistor and points below this resistor, they all belong to this piece of wire. So they are also at the same potential. So as a result, electric potential across this resistor and this resistor are the same. So I can...
Sorry, Professor. Could you explain how they're at the same potential if they have like the C node right there in between them? Because I understand how on the other side there's nothing inhibiting the potential.
junction point, that C node you said, yes, it changes what? It changes current. But when the resistors connected in parallel, they're not supposed to have the same current.
Right.
We're
Okay.
checking for the potential difference.
Okay.
Right? Yeah, this C point, yeah, it's an important junction point. But when you analyze electric potential, this C point is as good as this point or that point or this point or any of these points, right? You see, any of the points which are over in this bluish region, right? So all these points belong to this pieces of wire. And
Okay.
you remember,
Right.
potential the same, and exactly
Right.
the same
In
I can
parallel
say about,
circuits. Okay.
yeah. And all those points also belong to the same piece of wire, piece of metal, and of course their
That makes
potentials
sense.
are the
Okay.
same. Yeah,
Right.
of course.
But if
Yeah,
you took
current
like
changes.
right, because in parallel circuits the current is the summation of everything. But if it was a
Yeah,
series, then it wouldn't matter. Okay. All right,
yeah.
that makes sense. Thank
That's what we had over here. Over here, we did not have any junction points. There was no any nodes. So as a result, current is the same. So that's what I wrote, series, right?
you. That makes sense. Thank you.
Yeah, analysis is very simple, but you just need to get used to that, right? Okay, so then, yeah, those resistors are connected. But of course, this resistor, okay, if we sort of extend our analysis, for example, this resistor, it is not parallel to this one and that one. Why? Because this resistor gives us a potential difference as a result, additional potential difference as a result, potential difference across this resistor is not equal to this one and that one. All right, so this resistor is not in parallel to those two. So now I need to redraw it, and you know what, I will just move down. All right, so it will be point A. This resistor is, we did not disturb it. Then this resistor is still here. But then instead of these two guys, I'm going to draw one resistor, right? And I'm going to label it as R equivalent 2. R equivalent 2 instead of these two. And this is point C. This is point B. This is point B. This is point B. So R equivalent to, they in parallel, so I have to use these reciprocals. Oh, okay. So 1 over R equivalent 2 equals to 1 over R plus 1 over R equivalent 1. Right? So I can write it as 1 over R plus 1 over 2R. Right? Instead of R equivalent 1, I use this 2R. Okay, it's very simple. We just need to bring to the common denominator, right? So it will be, you probably use dark. 2 times 2. So common denominator, so it will be 3 over 2R. Right? 3 over 2 times R. And so now, of course, don't forget to flip, because what we just calculated, it's a 1 over R equivalent 2. So R equivalent 2 will be equal to 2 third of an R. So just flipped it. Whew. Okay, so now next. Now this resistor, and okay, I didn't label it R. These two guys, these two resistors in series, right? Because again, this is not a junction point anymore, right? We already collapsed all those resistors, so now just this resistor and this resistor in series, because current is flowing through them is going to be exactly the same. Because again, over here there is no junction point. Again, this is no longer a junction point. In the previous circuit, yeah, point B was a junction point, but once we collapsed these two resistors, so now that is not a junction point anymore. So current in R and current in R equivalent is going to be exactly the same.
Could I ask a question, Professor, again?
Yeah.
So when you have these resistors that are in diagonal that can trip a lot of people up, would the presence of a junction point be able to tell you whether two resistors would be in series or in parallel? Because I remember during the recitation class, there was a rule that, or a trick that we used to determine if resistors that were like diagonal were in series or parallel. But could like the presence of a junction point just automatically tell you if it's like if there's no junction point between two resistors, they're in series, but if there is, they're parallel?
Yeah. Yeah, exactly. So if there is no junction point between two resistors, then of course, when there is no junction point, current stays the same, conservation of current. But if there is a junction point, if at this point we had another wire going that way, for example, right? And let's say there would be some another resistor, then of course current through this resistor and that resistor would not be the same, because some current would flow that way, right? But since we don't have anything over here, right? So it's not a junction point. It's just a as any other point on this part of the on this wire, right? Yeah. So current is the same since there's no junction point.
Okay.
What you said is absolutely correct. Yeah.
Right. And then was the rule
In this
that
circuit,
we...
okay, just a second. In this circuit, point A and point C are the junction points. Yeah,
Right.
you connect here the battery, and of course, part current goes that way, and some current goes through this part of the circuit.
So rather than making an extra step and going R and REQ2, couldn't you just do the R in between A and C and REQ2 as being parallel, and then solve for REQ like
You
3
can say, of course,
directly?
you can combine two steps, and you can say this so that R and R equivalent in parallel with this resistor, with that resistor.
Oh, okay. So you can't just do like that R that's in between A and C. You can't just do that's in parallel with REQ2. You would have to do the
Hold it. I'm sorry. Let me clarify. Are you saying that this is in parallel with R equivalent?
Yeah, I was asking. Yeah, that's what I was asking.
No. This resistor and R equivalent are not in parallel.
Okay.
Because look, across R, this resistor, look, this point, okay, below this resistor R, is at exactly the same potential as point below this R equivalent 2. Yeah, these points are at the same electric potential. But look above this resistor. Point above this resistor R equivalent here, they have some potential. I don't know, maybe let's say 5 volts, right? This is 5 volts. But points above this resistor and these points are not at the same potential, because between these points and these points there is a resistor R.
Oh,
which
that makes
provide the
sense.
potential
Okay, yeah.
difference.
Right.
So
Okay.
potential difference is not going to be the same.
That makes sense.
You can
Okay.
say only that this resistor R is in parallel with this and that together.
That makes sense. Okay, I got it.
But it's better
yeah.
to make one step at a time. So first combine this resistor, claiming them as them being connected in series,
Okay. Yeah.
and that R equivalent 3 will be in parallel with R. Yeah, it's
Got it.
again, analysis are quite simple, but you just need to develop a habit of how to do it.
That makes sense. Yeah. Okay.
Awesome. All right. So now we need to calculate. Yeah, first of all, I need to write that these guys are in series. All right. Series. Okay, I didn't write that these guys are in parallel. So in series, and let me, okay, I'm moving randomly almost. Okay, so now I'll move this circuit to this part of the whiteboard. So this is our point A, point C, and this is R. And instead of these two guys, I will introduce resistor R equivalent 3. Right. And of course, we can calculate. They're in series, so it's trivial. So I can calculate R equivalent 3 equals to R plus R equivalent 2. So R equivalent to, it's a 2/3 and plus R. So it's R plus 2/3 of R. So it will be 5/3R. Again, bring to the common denominator, it will be 3/3 plus 2/3. It's a 5/3. So 5/3 times R. So that's the value of this. So in the final step, of course, now obviously no doubt that this resistor and these resistors are in parallel, because again, points above this, both of these resistors belong to this big piece of wire, so they are the same potential. Points below also belong to the same piece of wire, so and the same potential. So of course, if you subtract, you're going to get exactly the same potential differences. So now these guys are, of course, in parallel. Okay, and the final step, right, we can move down. So this is point A, and this will be our final R across between points A and C. Final equivalent resistance between points A and C. So that's what we wanted to find. So in parallel, so we need to take those reciprocals, right, to calculate. So it will be 1/R sub AC equals to 1/R plus 1/R equivalent 3. Okay, so 1/R plus, okay, R equivalent 3, it's that. So it will be 3/5R. 3/5R, right? I just flipped this plugging over here. So as a result, instead of 5R/3, it's a 3/5R. Okay, so we can bring to the common denominator. Of course, it will be 5R times, okay, let me remove this one. 5 divided by 5R. And again, we can add them. It will be 8 divided by 5R. And now, flipping, as a result, our final R equivalent, it will be 5/8 of an R. Okay, let me check. Yeah, in my notes, exactly the same. Yeah,
So
this
for the
uh,
sorry, I didn't mean to cut you off.
this example is more complicated, although you see collection of resistors exactly the same as in the quiz. But in the quiz, you calculated equivalent resistance between points B and C. It's sort of like a battery was connected to points B and C. Electrodes were connected to points B and C. And in that case, it was much simpler because these two resistors were connected in series, these two resistors in series. And once you collapse them, then you will have these, and that are connected in parallel. So that example is way, way simpler. In this situation, although configuration is the same, but if you connect the battery to a different points A and C, now equivalent resistor calculations are significantly more complicated. That's why I didn't give this example on the quiz, because you would spend the whole 15 minutes getting through this problem, only through this problem. Yeah, so what were you saying?
So I think you already answered it. So for the quiz that we had, then to calculate between B and C, we would go to step 2, but then also on the other side, on the left side as well, those two resistors would also be in series, and then it would be like a triple parallel. Okay.
Yeah, because of the symmetry, the distribution of resistors will be almost symmetrical, right? On the left side and the right side, so these two in series, those two in series, and then 3 resistors are in parallel. Were in parallel in that quiz, right? Yeah, much easier. So again, you see, it depends on how you connect, how you use this, I don't know, circuit, where you connect your battery or the rest of the circuit.
So if we were given to find out the resistance between points A and B, it will be the similar procedure that what you did just now, except it'll
Exactly the
be in a
same.
different way. Okay.
Yeah, exactly the same, right?
Okay.
Because of the symmetry, right? But the thing is, if you, for example, I didn't show that point, but if I would ask to calculate the equivalent resistance between points A and, for example, this point D, I can introduce point D, then the method of an equivalent resistance wouldn't be applicable here, because none of the resistors would be connected neither in series nor in parallel. But in that case, there is another trick which can be used, right, by using the symmetry of the problem. But we're not going to discuss that. It's since we didn't emphasize on that in the recitation classes on using some tricks, so I'm not going to do that. Okay, these okay, we discussed. Okay, so now let's look at another example about the equivalent resistances. But now we will have to fully analyze the circuit. We will have to analyze and find all the currents and potential differences using method of an equivalent resistance. And I'm going to discuss this example. It's similar to this method like you had in your quiz, right? But since we didn't have a quiz, we did not have a quiz about applying this method for resistors, so I decided to discuss it now. Okay, so this will be now problem number 7. Problem number 7. And we're still in this box. We're still in this area. Then will be Kirchhoff rules and power. As I said, RC circuits we're not going to review because you're still doing your homework, which means it's still fresh in your heads. Okay, so for this problem, I will need the whole whiteboard, so I need to properly arrange space. So, you remember, these type of problems are usually solved in this way. First, I'm going to draw 3 diagrams on top of each other. There will be first diagram over here, then here and there. Then I'm going to write something on the right, but less. And lots of writing is going to be on the left side of those diagrams. Okay, so let me start drawing those diagrams. I think it should be enough. Okay, yeah. So here I have a battery. Then there is a resistor. Then there is another resistor. Then there are 2 resistors connected like this. And then the whole thing, and they are connected to the rest of the circuit like this. Okay, now let me write the numbers. Potential difference across the battery. You know what? Yeah, I'm afraid that I will need this space. Let me write above. So delta V, potential difference across the battery is 24 volts. Oh my God, finally, in this book, there's a problem where the battery doesn't have 9 volts potential difference. Here it's a 24. Then, this will be my R1, R2, and I will write values over there. Then R3 and R. Oh my God, in my notes, I was labeling resistors and I missed R4. I used R5 immediately. All right, since I'm going to send you my notes, let me also follow my notes so that students wouldn't be confused between what is in the video and what is in my notes. So for whatever reasons, I forgot to write R4, use R4. So immediately I switched to R5. There is no resistor R4. Okay, I don't know how it happened. I was just preparing in the morning, so and only now I noticed that there is no R4. But again, it's not a crime. So now let me give you the numbers. So R1 is, where is my R1? 6 ohms. Then R2 is, it's this one, 12 ohms. Then R3, this is 4 ohms. And R5 is 2 ohms. Okay, that's what is given, and the problem is just about we need to analyze this circuit. Again, what does it mean? What does it mean analyzing a circuit full of resistors? 3 parameters: R, I, delta V. All the resistances are given, so we just need to find potential differences across all of those resistors and currents flowing through all those resistors. Okay, so
This
now
isn't really, sorry, this isn't really relatable. Why does it go 1, 2, 3, 5 for the numbers of
okay,
resistors?
I didn't get. So what do you mean? What? Say it again.
So this doesn't have anything to do with the question. This is just kind of like how it was drawn out. Why are the resistors numbered 1, 2, 3, and then 5?
I can't. You're asking why it's not R4?
Yeah, pretty much.
Okay, I cannot answer because when I was preparing this problem, for whatever reasons, I jumped over R4 and used R5 immediately.
Oh, okay.
I don't know. It's just
okay.
I
No,
cannot answer.
I didn't have a
Just,
question about I didn't have a question about like what we were doing so far. It was just seemed a little strange.
yeah, it's strange, right? Since I prepared in the morning and only now I noticed that R4 was kind of missing, right? But again, it's not a big deal. You can label it any way you want, right? So I can say my soul desperately wants to use R5 instead of R4. It's not a crime, right? You agree? Of course it's strange, but again, I notice only now, but I don't want to change it now in the because I'm recording it. And then when students will start comparing my notes, because I'm planning to send them with the video, they might be confused. So that's why I don't want to change it now, although I can do it easily.
That makes sense. Okay.
Yeah. All right. So, yeah, what needs to be found? I wanted to write. So let's find all currents, I1, 2, 3, 5, right? There's no 4, and potential differences. All right, delta V, 1, 2, 3, 5. I'm still human, right? Of course, yeah, I wish not to make any of these, all right, okay, not mistakes, but silly things, but it happens. Right, okay, so procedure, very, very similar to the procedure which you use in your quiz analyzing capacitors. Now we need to do the same with the resistors. Basically, we just need to use this box and that box. First, we need to simplify this circuit to the simplest possible, where we will have only a battery and one resistor. And then we will start moving backward, finding what needs to be found over here. But first, let's simplify. So let's see which resistors are connected either in series or in parallel. In this case, it's actually these two guys, R5 and R3, are connected in what? In series, because between them there is no junction point. So current is the same. So R5 and R3 are in series. So let me put them in the right. They are in series. And at the same time, these two guys, but now these two guys, of course, connected in parallel because potential differences are the same. Points, all the points above these two resistors are the same potential, and points below these two resistors also are the same potential, right? Because any points of the wire are at the same potential. Right. So potential differences are the same, so it means that these guys are connected in parallel. So you see, we can make two steps simultaneously in one step, or two changes, right? Right, so now let me first redraw this circuit and then I will calculate. So, of course, battery works in exactly the same way. Instead of those two resistors, I can introduce R35, right? And instead of these two resistors, I can introduce R12. Again, battery still has the same potential difference. Okay, so now let me calculate R35 and R12. First, I will calculate R35 because it's easier. Right, so let me write it here. R35 equals to R3 plus R5 because they're in series. In series, we just need to add values. It's easy. All right, so if you add values, okay, I will write underneath. 3, 4, 5, 2, so it will be 6 ohms. Right, so that will be the value of R35. Now, R1, 2, and of course now we need to take 1 over R's. So it will be 1 over R1, 2 equals to 1 over R1 plus 1 over R2. And, okay, I'm not going to bring to the common denominator and so on. I will just look at my notes and write down the value of R1, 2, right? I doubt that you will argue about this or disagree because you can easily calculate this. Right, so it's 4 ohms. Right. Although in the quiz, in the previous quiz, right, which we had just recently, some students made some mistakes when they were calculating these reciprocals. Right? Silly mistakes, really. All right, so now we know everything about this, and so now the next step, obviously, since there are no any junction points between these two resistors, right? So current is exactly the same. So it means that these two resistors, of course, connected in a series. Currents are the same. So we can, as a result, simplify our circuit to the simplest possible. So battery and R final R equivalent. Right. In series, so we just need to add this plus the, oh, actually, nice numbers. 10 ohms we're going to get. So R equivalent equals to R12 plus R35 equals to 4 plus 6 equals 10 ohms. Right? Let me check. Yeah, 10 ohms. So now, the simplest possible circuit, we know potential difference, delta V 24 volts. We know resistance. Of course, we can calculate the total current taking from the battery. All right. So we can calculate the total current. And that will be I equals to delta V divided by R equivalent. So which is 24 volts divided by 10 ohms. 2.4 amps. Right. So I equals to 2.4 amperes. Okay, so this is a very important step again. So this is the current in this circuit I, right? But at the same time, you remember when you introduce R equivalent, the rest of the circuit works in exactly the same way. So it means that the same current is here and the same current, total current, is over here, taking from the battery. And then, of course, it will be split. So this is I, and this is, of course, the same I. So now we found at least something. Usually I compare at this point as like making a crack in the wall, right? And then you can just increase that crack, right? And reveal what is unknown slowly, right? Step by step. So now once you know this, now we can start moving back using these pieces of physics in order to find what needs to be found. So now let's start moving back. So first step. This resistor replaced two resistors connected in series. And so what is true in series piece of physics? In series, current in the equivalent resistor equals to the currents in resistors connected in series. So it means that this current through the equivalent resistor equals to the current flowing through this resistor and that resistor. Okay, so this will be the bridge, first bridge. So I can write that this current I, okay, I will need space over there. So I equals to I12 equals to I35 and equals to the current, total current, which we just found, 2.4 amps. Right, so that's the first bridge which I need in order to find the first set of unknowns. Okay, we will see what we will be able to find. All right. So now we know current flowing through this resistor R12. We know the value of R12 4 ohms. Of course, we can find potential difference using Ohm's law, right? Delta V will be equals R times I. Right. So now we can write, so delta V 12 across the resistor R12 equals to R12 times I12. So pretty much the value of current comes from the bridge, right? So R12, where is it? 4 ohms. So 4 ohms times current 2.4 ohms. Oh, amps, sorry. 2.4 amps. So it will be 9.6 volts if you multiply them, right? 9.6 volts. So that's the potential difference across the resistor R12. Right. Okay, so then next we can find potential difference across R35. But actually you can calculate even easier. 24 minus 9.6, it will be the value of the potential difference. But I'm still going to use the Ohm's law to calculate potential difference. Again, current we know, resistance we also calculated, so we can calculate the potential difference. So delta V across the resistor 3.5 equals to the value of resistor times the current. Again, the value of the current comes from the bridge. Right. So R35 6 ohms, right, times current, current 2.4 amps, and if you multiply, it will be 12 plus 2.4, it will be 14.4 volts. 14.4 volts. Let me check. Yeah, 14.4 volts. And you know what? There's overlapping about this part and that part. Let me separate them. Okay. So pretty much we exhausted everything that we can using this bridge, but still we didn't find anything from our unknowns. But the last step will be very, very fruitful in terms of finding our unknowns. So now, when we move, yeah, we're already here. So now we need to move from this circuit to that circuit. And so yeah, now we will have to use two bridges pretty much to move from this circuit to that, two bridges, because R12 replaced these two resistors in parallel. So it means that potential difference across R12 will be equal to the potential difference across the first resistor and potential difference across the second resistor. But at the same time, these R35 replace two resistors connected in series. So at the same time, we can use this fact that currents must be the same. So let me do it step by step. First, which one I analyze? Okay, I use R12. Okay, so let's use first R12 and then R35 to reveal what needs to be revealed. So first, I will use, as I said, this. So it's a delta V12, which we just found over here, right? Delta V across resistor R12 equals to the potential differences across this resistor and that resistor. So it's a delta V1 equals to delta V2, and it is equal to 9.6 volts. 9.6 volts. Okay, so that's bridge for this step. And of course, using this bridge, we will be able to find two currents through resistors R1 and R2. How? R1 is given, potential difference across R1 is given. So of course, we can find current, the electric current using Ohm's law. So I1 equals to delta V1 divided by R1. And of course, delta V1 comes from the bridge. Delta V1 9.6 volts divided by R1. Where is my R1? 6 ohms. 6 ohms. And okay, it will be 1.6, it looks like 1.6 amps, right? Let me check. Yeah, 1.6 amps. So finally, we found at least something about, actually, now we finished analyzing resistor R1 because what? Value of R1 is given. Over here, we found the potential difference across R1, and now we found current through R1. So we finished analyzing resistor R1, right? So now let's do the same about resistor R2, finding its current. By finding its current, all right, so again, it will be 9.6 volts. It basically comes from the bridge again, right? And now divided by, what's the value of R2? 12 ohms. Okay, no way, I'm not going to calculate that in my head. I need to look at my notes. 0.8 amps, 0.8 amps. Okay, so now we finished analyzing resistors R1 and R2, but we still don't know potential differences and currents through R1, I mean R5 and R3, but we still, that information is still hidden in R35. So this replaced those connected in series, so it means that currents are the same. Current through resistor 3.5, right, equals to, okay, no, wrong color. So current through this resistor, I3.5 equals to currents through this and that. So I3 equals to I5, and I3.5, it's at the very beginning here in the first bridge. That information is here. It's a 2.5 amps. 2.4. I said 2.5. No, 2.4 amps. So now we use the bridge, this one. And so now, if you know current through this resistor, the value of the resistor is given. Of course, using Ohm's law, we can find potential difference. Piece of cake. Right. So delta V3 equals to I sub 3 times R3. So current 2.4 amps times resistance 4 ohms. So 8 plus 1.6, 9.6 volts, right? Let me check. Yeah, 9.6 volts. 9.6 volts. So we finished analyzing resistor R3. And now the last step, the last push, R5. So delta V5 equals to I5 times R5. I5 again from the bridge. Resistance is given, so it will be 2.4 amps times R5. Where is my R5? 2 ohms. 2 ohms. 4.8 volts. Okay, done. And again, yeah, as I said before we started solving this problem, of course, the procedure is very similar to the procedure which you used in the quiz, analyzing C equivalents. I mean, you analyzing capacitors connected in series or in parallel. Of course, except for formulas slightly different. But the ideas are the same. Ideas are the same. Yeah. Okay, let me get some water. Okay, so yeah, maybe another 15-20 minutes and we will finish this. again, why I decided to discuss this, because we did not have a quiz. I usually give a quiz either about using analyzing capacitors or resistors. Since I analyzed capacitor, we had a quiz about capacitors, so I decided to analyze here resistors. Okay, so let's discuss Kirchhoff rules, and then one example about power, and we'll call it a day, right? Yeah. Okay, if you're not objecting, then I will start erasing. So this will be number 7, problem number 7. Okay, so multi-loop circuit. Okay, two-loop circuit, basically, two-loop circuit. Okay, I will grab my notes and let me draw that circuit. So first we have a battery here. Yeah. Then over here there is a resistor. Then I hope you're not hearing my neighbors. They have a loud conversation. No, they're not quarreling, just loud conversation. Right. Then there's a resistor over here. Or there's another battery inserted in this part of the circuit, right? Then there is a resistor in this branch. Then a battery again. And a resistor. Yeah, and connected like this. Okay, so now let me label. EMF1, then this will be EMF2 and EMF3. And resistors. R1, then R2, this is R3, and this will be our R4, and this one is R5. Okay. Actually, I gave in numbers. Okay, let me write at the top also numbers. So EMF1 is 3 volts. The other two batteries are the same. EMF2 equals to EMF3 equals to 6 volts. Resistors. 4 resistors the same. So R1, 2, 3, 4 equals to 2 ohms. And the number 5 is different. R5 equals to 4 ohms. Okay, so we need to analyze this circuit. Of course, in this case, basically means we need to find currents flowing through all these 5 resistors. And again, if you find the currents, then finding potential difference is a piece of cake using Ohm's law. If you know current through this resistor multiplied by resistance, of course, you will get the potential difference. Then the same over here. Then the same here, there. Once you know currents flowing through all the resistors. Okay, and look, guys, none of these resistors are connected in series or in parallel. None. For example, this and this, they are not in series because here there's a junction point, current changes, right? Then this and this, they are not in parallel because here there's a battery which is going to give different potential above this point at that point, plus a resistor is going to mess up, right? Then what else? Pretty much you can pick any 2 resistors and currents are not the same, potential difference are not the same. So it means that the method of an equivalent resistance is not applicable here, period. But we have Kirchhoff rules, which are universal because behind them we just use universal laws, conservation of charge and conservation of energy, right? So let's use Kirchhoff rules. And you remember, every time we use 3 preliminary steps, okay, we have to make 3 preliminary steps, sort of like a preparation before we can start writing equations. Of course, on the exam, you don't have to write, if you just start writing equations, yeah, I will believe you. You don't have to write those preliminary steps, but you need to show everything that needs to be shown in the diagram. So it means that directions of currents, direction of travel, and junction points, and so on. So first step, preliminary steps. 3 preliminary steps. So first one, identify junction points. I will just write junction points. Junction points. In our case, okay, I usually label them A and B. I think the upper one is A, yeah. So this is A and this is B. So junction points A and B. Again, you remember, at junction points, currents change, and currents change. So it means that if we look at this part of the circuit between point A and B, but in this part of the circuit, there are no any other junction points. So it means that in this part of the circuit, current must be the same. Current stays the same. So we can label it. Well, we can give it a name. Okay, I don't remember. I will just look at notes. Which current? I think it's I1. Yeah, I1. Direction, it's up to you. We cannot justify we pretty much we cannot tell which direction is going to be a correct direction, because basically, look, we have a fight of 3 batteries. This battery is trying to drive current that way. This battery is trying to drive current this way and that way. This battery is driving the current that way. It's a big mass. So of course, it's almost next to impossible to tell immediately which directions are correct. So let's assume. So don't sweat, just pick any directions. In my notes, I picked this direction. So I picked this direction. So this will be my current I1. Right, from point A to point B. Let me check. Yeah, that's the direction of current I1 I pick. So as the second preliminary step, we just need to introduce currents in directions. Currents in directions. Currents and their directions. Their directions. Right? So now, between point A and B, in this part of the circuit, also current must be the same. Which way, up or down, we don't know. Let's just assume, and I will look at my notes, which directions I pick. Okay, down. Right, so let's say I pick this. This is my second current, I2. And then in exactly the same way, so in between points A and B, in this part of the circuit, current must be the same. I3, this way, this direction, or that direction, it doesn't matter. I picked this way, counterclockwise. So that will be I3. Okay, so second preliminary step is done. And the last one, you need to pick a travel direction, right? In order to know which points are final, which points are initial, when you start calculating delta V's, potential differences across each element. Again, which direction, it doesn't matter. Clockwise, counterclockwise, it really doesn't matter, but you need to pick a direction. I picked in both cases counterclockwise. So this is loop 1 travel direction, and in the same direction I will pick for the loop 2. Loop 2, this is my travel direction. Okay, so now let me write that I've made the second step, the last step. So travel directions. Travel directions. Right. Okay, so now after this, we are ready to start writing down all equations. We have 3 unknowns, I1, I2, and I3. So we need to find them. And of course, in order to find them, we need to write down 3 equations. And you know what? I will write over here. So I1, I2, and I3, these are our unknowns. Right? Okay, so let's start. First, junction rule. Usually students have No troubles with that equation, except for sometimes students just forget to apply a junction rule. So junction rule, right? For point A, junction point A. So all the currents in must be equal to the total amount of current leaving the junction point at point A. In I3, that's it, leaving I1 and I2. So for junction point A, so it will be I3 equals to I1 plus I3. For junction point B, similar. In I2 and I1, I2. Guys. I'm surprised that you haven't started screaming at me. Of course, this is I2. I said I2. Okay, I hope I said I2, but I wrote I3. Right, this current. So now, junction point B in I2, I1 plus I2, and it is equal to I3, which leaves junction point B, so I3. Of course, as you remember, all the time, one equation about one junction point is redundant. In this case, one of this equation is redundant because we have two exactly the same equations. So let's dump equation number B. So we have only one equation, but at the same time we still have loop rule. Now loop rule, right? And first for loop 1, right, equation, and then for loop 2. Loop 1, so this one. You can start counting potential differences from any point. I usually start counting, start moving. My starting point is just before the battery. I like crossing battery first. Again, just my minor compulsion, as I told you in my lectures. So I will start from this point. So this will be my starting point. So this is our travel direction. So first I move across the battery from plus, right, to minus. From plus to minus. You remember our rules, mnemonic rules, which we introduced in the lecture, right? If you travel across the battery from minus to plus, contribution is positive, plus EMF. If you travel from plus to minus, potential drops. Of course, contribution to the loop equation is negative, and absolute value of that contribution is EMF. So in this case, it's a minus EMF 1. So minus EMF 1. Usually, okay, not usually, I don't give those mnemonic rules in the formula sheet. No way. If you forget about them, you can easily restore them by just analyzing the way we analyzed in the lecture. Or just remember, and usually it's easy to remember once you do a couple of examples of this type. They're in your head, those rules. So now, after this battery, we need to cross this resistor. Travel direction that way, current direction I1 also that way. So directions are the same. Rule number 3 about the resistor, contribution is negative. So it's a minus I1 times R4. So minus I1 times R4. Then after this, we need to go up across this battery. When we move across the battery, so we travel from minus to plus. Rule number 1, contribution is positive. So plus EMF 2. Plus EMF 2. Then resistor R5. Travel up, current down. So directions are opposite across the resistor R3. Travel direction and current direction. So in the case of opposite directions, it's a rule number 4. Contribution is positive. In this case, it's a plus I2, because that's the current flowing through this resistor, times R5. So plus I2 times R5. And after this, we have to cross this resistor. Okay, let's see directions, at the directions. Current direction that, travel direction that way. So both directions are the same. So rule number 3, contribution is negative. So it's a minus I1 R1. Minus I1 R1. And I'm back to the initial point, my starting point. So now I need to complete the equation. Right, it is equal to 0. Don't skip that. because that's a mistake, basically, right? We're all science majors, and of course you understand equation must look like an equation, right? Not just bunch of terms, right? So equation number 2. So 1, 2, and we have loop number the second loop. So let's write similar for the loop number 2. Right, loop 2. Okay, so now where should I start? Where I started? I think I started just before epsilon 3. Yeah. So let me start over here. And this is our travel direction. So this is my starting point. And first I need to cross this battery with the EMF, with the potential difference EMF 3. Right, so starting point. So we travel from minus to plus. Rule number 1, when you travel across the battery from minus to plus, potential goes up. So contribution is positive, plus EMF 3. Plus EMF 3. Then we face this resistor. Current direction I3 that way. Travel direction also that way. So both directions are the same. Rule number 3, negative. Minus I3 times R2. So minus I3 times R2. Next, so this resistor, travel direction down, again, this travel direction down, current I2 also down. So both directions are the same. Again, contribution is negative, so it will be minus I2 R5. So minus I2 R5. Then, okay, this battery, so we travel, you see, from a plus to minus. When you travel from plus to minus, potential drops, right? So that's rule number 2, our contribution is negative. So minus EMF 2. Minus EMF 2. And after this, we go this way. So now this resistor R3. So travel direction up, current direction also up. Directions are the same. Again, negative contribution. R3, I3. So minus I3 times R3. And we're back to the starting point. So we completed the loop. So it must be equal to 0. So equation number 3. The third equation. So that's it. So pretty much 3 equations, 3 unknowns. Usually on the exam, I don't ask to calculate, because again, if you start calculating using sort of like a brute force, doing it manually on a piece of paper, it would take you 15-20 minutes, and still you can easily make some mistakes, algebraic mistakes. But of course, calculators can be easily used to calculate this. So usually I ask just for the equations, all necessary equations. And so in this case, I can actually write down the answers, numbers, in order to analyze directions of current. So let me write down. So if you calculate it all, if you calculate currents, solve these equations, I1 will be equal to 0.5 amps. So it means what? Absolute value of the current is 0.5, and this is the correct direction for the current I1. So current is going to flow from point A to point B through this part of the circuit. So direction is correct. Then I2, this current I2 is minus negative 0.25 amps. It means what? It means that the absolute value of the current is 0.25. Minus just indicates that my assumption about current direction, this I2 direction, is wrong. So this current I2 actually flows up through this resistor, right? So which way I wrote? I2 direction is opposite. So I2 is up. So I2 is up, right? Opposite direction. Opposite direction. Opposite to the direction which I assume. So actual direction of I2 is up. Right. I3 is I3 equals 0.25 amps. So current is positive. It means that this is the correct direction for the current I3 in absolute, and the value of the current is 0.25. Okay. Yeah, these problems are not that bad, right? Again, you just need to remember those rules, and then it's very, very mechanical, right? Usually it should take you, I don't know, a few minutes to finish the problem of this type. And of course, you don't have to write these preliminary steps, right? So everything must be on the diagram. And usually on the exam, I give all these directions. Direction of the current, direction, travel direction, and here's the reason why. Because I remember in my first semester when I started teaching this course, I didn't give any directions on the exam paper, and I assigned my ATA, my TA, to grade that problem. And after half an hour, he came to my office. Okay, I don't want to say what he exactly said, right? But he was very, very unhappy about this, right? Because he had to sit and carefully look at all your directions, because everyone was speaking different directions, right? And then he had to sit and carefully look at all those directions and check each term. It was it was a ridiculous amount of work. So of course I realized that was my mistake. So when I finished grading my problem, I started helping him, right? So, and after that, all the time, if I give a problem like this, all travel directions are given, all current directions are given, right? So that you just need to write these terms, and then it's much faster for us to grade. Otherwise, it's an insane amount of tedious work, right? Okay, so if guys you have any questions, if something is not clear, just tell me, right?
Professor, question.
Yeah.
So for like problems like these, when we use the loop rule, we just have to make sure we go in the direction of current to get the equations.
No. You're not following the direction of current. You're following direction of your travel direction.
Okay.
But of course, you need to know the current direction when you analyze resistors. But when you analyze batteries, you don't need current directions. So you follow the travel direction. If you start from this point, you move this in a counterclockwise direction. If you start from this point, still counterclockwise direction. If you start from here, still counterclockwise. But of course, if you pick a clockwise direction, okay, follow that direction. It's not going to change anything. Look, guys, actually, what is going to change if you pick a different travel direction? Let's say instead of counterclockwise, let's say you pick clockwise. The only difference in the equations will be, instead of this minus, you're going to have plus. Instead of this minus, plus. Instead of this plus, minus, minus, plus. So effectively, equation is the same, but all the signs are going to be changed. It's sort of basically like multiplying the whole equation by -1. But if you multiply equation by -1, equation is effectively the same, right? If you write a minus b equals 0, or write minus a plus b equals 0, the equations are the same, right? So that's the difference if you choose a different travel direction, right? So that's why I keep telling you, don't think which direction to pick, just pick any direction and stay with that direction. So
Could
follow
you?
travel
Oh,
direction.
sorry.
Yeah.
So I just had. So I understand the loop rules when you're going through the battery, but can you just re-explain the two loop rules pertaining to the resistors? Like after you pack the battery from the positive side and you're going through it in your travel direction, because I remember you drew it out during our recitation class.
I cannot say that I understood actually the question. Can you just again repeat it, and I will and I will concentrate more.
So
yeah.
I understand the EMFs, when you were going through the loop rules, if we're just looking at loop 1, I understand the EMFs where you went from positive to negative, that was where it would be negative. Can you just explain when you were going through the resistors, I1 times R4 is negative, but I2 times R5 is positive?
You're talking about this and that, for
Yeah,
example.
for
So
loop
why
one. Yeah,
do
for
we have
loop one.
here minus and here plus? Okay.
Yeah, just to like
It's basically-
reiterate the rules.
Yeah. We've done it in the lecture. Okay, let me just repeat that. Actually, I can use this part of the board where are my markers here. Okay, so let me draw one of the resistors, right? And let's assume that travel direction is this. Okay, I usually use blue. Let me use blue. So let's say this is our travel, right? Okay, travel direction, it means that this is our final point, right? And this is our initial point, right? And so again, what we are calculating, we're calculating delta V. Delta V, which is V final by definition all the time, minus V initial, right? Okay, let me separate it like this. So now, next, to analyze a resistors like we discussed in the lecture, you also need to assume a current direction, because at this point we don't know, we have no idea which point is at higher potential and which point is at the lower potential, this or that, because we just don't have that information, nothing about that. So pretty much it's sort of like a dead end. So if we don't assume a current direction, we wouldn't be able to move any further. So that's why every time in one of the steps we pick a current directions. So let's assume that we pick this current direction. So that's our current. Assumes our assumption. Okay, if we assume this current direction, of course, you know that current flows from plus to minus, from regions with higher electric potential to the regions with lower electric potential. So if current direction this way, it means that here we have higher electric potentials. Electric potential is higher, and here electric potentials is lower. Okay, is lower, right? So here I can write V plus, and here I can write V minus. Again, V plus, it means higher, V minus means lower, right? So now we see we want to subtract V final minus V initial. So our final point is here. And we see it is at lower potential than initial point, right? So I can write this is V final point, V minus, and minus initial point, this initial point is at higher potential. So minus V plus. So if you subtract larger number from smaller number, for example, let's say this is 5, this is 3. 3 minus 5, of course, the contribution is going to be negative. So our contribution to the equation is going to be negative. But what's the absolute value of that contribution? Usually resistance is given. The value of the resistance is given, let's say R, right? And current is our unknown. So absolute value of that contribution is IR, but with minus. Minus I times R, right? So now, instead of making this, 3 or 4 steps in order to get to this conclusion, we develop a mnemonic rule. If current direction and travel directions are the same, like what we have here, contribution to the loop equation is negative, minus current flowing through the resistor times the value of the resistor. So that's the logic why over here we had minus, because in this resistor R4, where is R4? Here. Current I1, you see current I1 goes that way. And at the same time, travel direction, you see, also that way. So both directions are the same. It's this situation. Contribution is negative, minus IR. Oh, here, minus I1, R1, R4.
That makes a lot of sense. Okay, thank you.
You're recalling?
Yes, I understand now.
We discussed that in our lectures, and then I refreshed in the recitation classes.
Right,
and of
no,
course,
that makes a lot of sense now.
You obviously see that if directions are opposite, right? It
then it would be positive, right?
Logically follows. So of course, contribution is going to be positive. But of course,
right,
you
that
can
makes
convince yourself. You can convince yourself repeating similar steps.
Okay, thank you.
Okay, yeah. Mm-hmm.
Professor, just one more question.
Yeah.
If your you have your I2 direction pointed in downward, but if it was upward direction, what would be the loop 1 equation be?
loop 1 equation, if this is up, loop
Yeah.
1, this. Okay, this is going to be the same. Pretty much there will be only one term different related to resistor R5. So this will be the same. This will be the same because the current I2 has nothing to do with this term. AMF2 will be the same because when you analyze batteries, you don't care about current directions. You only look at travel directions. Travel direction, if you change the direction of I2, travel direction is still the same. There will be only one change in this term. So if your current direction is up, if your current direction were up, then travel direction is up, right? Travel, you see travel up. Your current would be also up. So both directions, current and travel through the resistor R5 are the same, would be the same, right? And it means that directions are the same. It means that you would have minus over here, minus I2 R5. So that will be the only change in your equation, loop 1 equation. You see that?
Slides, and I could see the difference. So which is why I was confused before. Yeah, but it makes sense.
Makes sense. Okay, good.
Yep.
There will be difference only in one term. This will be also the same. Yeah, everything will be the same. The rest will be the same. But of course, at the same time, loop 2 equation would look different slightly. So that's why, as a result, and of course, even junction rule would look different, right? I mean, junction rule equation would look different because in that case, if I2 is up, then we would have I2 is in, I3 in, so we will have here I2 plus I3 equals to I1. So all three equations would be changed, would have different look. But the answer at the end will be pretty much the same, except for, of course, you're going to have plus over here. Your answer for I2 is going to be positive because your direction is going to be the correct direction. Right?
Okay, got it now. Thank you.
Okay, so the final push, the final problem, a little bit about power. Just to finalize. Oh, it's already almost 3 hours. Huh. 1, 2, yeah. Well, time flies. So now I will erase this. Problem number 8. 3 bulbs connected in this way to a battery. Okay, let me draw the circuit. All right, so battery, then a bulb. Okay, I'm going to draw a bulb like this. And here. That's bulb number. Okay, it's A, bulb A. Then there will be 2 other bulbs, right? So one is here. Right, and the other bulb will be here. Okay, it looks like my neighbors are getting loud, but still, it's just a conversation. And they speak in Spanish, so I don't understand anything. All right, so EMF. And then this resistor. Okay, bulb. Of course, bulb is just a resistor which produces light, but effectively just a resistor. So let's say resistance is R, and let's label this bulb as A. These 2 bulbs, again, they have the same resistances, R, and this is bulb B, and this is bulb C. But they have basically identical bulbs, 3 identical bulbs. Identical bulbs. And so resistances are the same. Okay, let me say something. Okay, I'll just write R. Right. Okay, so we need to answer the simple question. Which bulb, actually we just need to rank in order from most to least the brightness of all these three bulbs, right? I can say compare brightness. Let's compare brightness. Right. So production of light is basically conversion of what? Electric form of energy into light. Conversion, right? Transformations, right? You remember our lecture about the power, right? So we basically need to compare powers, right? PA, PB, and PC. We just need to compare them, right? And of course, you remember, over here, three ways of calculation. Well, if sometimes it's more convenient to use this, sometimes more convenient to use that, and sometimes more convenient to use that formula, right? In this situation, I think more convenient to use this, I squared times R, because resistances we know, right? And now let's just look what happens to currents. Current, let's say, I. Let's say current I leaves the battery, right? And of course, this current is going to flow through this resistor. Okay, this bulb. Let's label it current I. Then, what happens to this current I? Of course, we don't know it right now, although we can easily calculate it, right? What happens to that current I at this junction point? Okay, let me emphasize that this is, of course, junction point. Of course, that current will be split, right? These bulbs are going to split this current. And of course, since this bulb, resistance of this bulb equals to the resistance of that bulb, of course, they're going to split equally. Complete equality, right? So this current I, of course, going to be split. And half of that will go this way and half of that go that way. So current through this resistor is going to be I over 2, and current through this resistor is going to be also I over 2. Right? So it means that if we use the formula which I just said, the most convenient probably I squared times R, P equals I squared times R. And of course I can write that PA will be equal, power through this bulb will be what? Current I times R squared, right? Then PB, power through bulb B. The same formula, but now current is I over 2 squared. Oh, no. What, damn it. Wait, guys, sorry. Why? I wrote I squared times R, but I don't know why I changed over here. Well, probably after 3 hours of yapping, right? I can justify it. Right, so here I divided by 2 squared times R. So it will be I squared R divided by 4. So the power through bulb B is going to be smaller than power produced by bulb A by a factor of 4. So only quarter of the power will be produced in bulb B relative to bulb A. And of course, the same story in bulb C, right? Because bulb B and C are in exactly the same conditions. At exactly the same conditions. So it will be, so I can write this is P A divided by 4, and of course here the same PA divided by 4. Okay, it doesn't look like A divided by 4, right? So of course, if we compare them, of course, power through bulb A is going to be larger than power through bulb B, which is equal to the power through bulb C. Basically, we didn't spend much time discussing powers in the lectures and the recitation classes because basically regular analysis of the circuit, and then at the end, once you found all the electrical parameters like current or potential differences, right? It depends what is given in the problem or what you found. You just make a decision which formula is the most convenient, and use it and compare or do whatever needs to be done to solve the problem, right?
So just to confirm, if we're treating the bulbs just essentially as resistors, then
Yeah.
for B and C, the current would be divided by 2 because that's the conservation of current in parallel resistors. So they would have to be like half of them.
No, it's basically of course you use conservation of current. Conservation of current because at this point current gets split, right? But we use the symmetry.
Oh, okay,
right?
okay.
These bulb B and bulb C are at exactly the same condition. So when electron comes to this point, and it has to make a decision which way to go. It doesn't have any preferences because it will be equally easy or equally difficult either going this way or that way. But if we, for example, let's say we remove this bulb C and just put just a piece of wire, so no resistance instead of C, no resistance. So where would the electron go when it comes to this junction?
It would always go to C because there's no resistance there.
Okay, of course, because in that case, yeah, electrons, although they don't have brain, but they are very smart, practically.
Okay, so then,
smart, right?
So then, if the light bulb C was replaced with just a wire, then technically the current at B would be 0 because it would always go to C.
Yeah, yeah.
Okay.
The current will be completely 0, and that bulb will be useless without doing anything.
Okay.
And actually, the next part, that's why I drew this line. I actually wanted to discuss the situation similar to what we just analyzed or discussed. Look, what if you take I was planning about discussing, what if you take piece of wire and connect this point with this point? This is just a wire. What would be different in terms of these powers? And now we just discussed it, right? When electron comes to this junction point, it has now 3 options: either traveling through through bulb B, or through bulb C, or through the no resistance. Of course, electrons are smart enough. Of course, instead of crashing their heads through these resistors, right, resistances, producing something, doing some work, who wants to do that? Of course, there's an easy way of skipping all the works. Of course, all the electrons are going to travel through the wire. As a result, no current will be flow through bulb B and bulb C, and of course, both of these bulbs wouldn't produce any light, so they will be dark, because right. So we just jump ahead slightly before the question which I wanted to add to this question. Right. Make sense?
Yep.
Okay. Okay, it should be enough. It should be enough, and yeah, it's exactly 7:35. Yeah, exactly 3 hours because we started like a few minutes later. Right? I thought we would finish a little bit earlier. Okay, guys. So as I said, yeah, it's enough for today. RC circuits. I decided not to discuss anything because you're doing homework right now, right? And we had our recitation classes and lectures, so these should be fresh for you, right? And again, the problems are reasonably simple because most of the time you have a function how charge changes in time in RC circuit, discharging or charging, or current changes in time. And most of the time there are 2 types of problems, right? So either time is given and you need to find the value of whatever charge or current at a certain moment of time, or the value of charge or current is given and you need to know when that happens actually. So you just need to find time. Okay, invert that function and solve it for t, right? And of course, all the time you also need to calculate time constant of this or that circuit. Okay, guys. So if you have questions, you can ask. All right. If not, then we can call it a day, right? And I will start making a video out of this exam review session.